If you want to decentralize AI inference today, the problem is essentially solved. When a user sends a prompt, that request is entirely independent. You can shard those individual queries across thousands of dispersed GPUs with minimal coordination. But training a model is a completely different engineering problem. For years, the absolute consensus across the machine learning industry has been that serious training requires specialized hardware sitting under a single roof. The math behind that assumption comes down to raw payload. Take a 70 billion parameter model. Running that in mixed precision requires roughly 140 gigabytes just to hold the weights. Once you add in the optimizer states and activations, the total memory requirement pushes up to between 400 and 600 gigabytes. A single NVIDIA H100 GPU only has 80 gigabytes of memory. That strict physical limit dictates that you have to split your workload across a multi-GPU architecture, regardless of whether you are in a centralized facility or a distributed network. And when you train across multiple GPUs, every single chip needs to know exactly what every other chip just learned. They have to constantly synchronize their computed gradients thousands of times per step for weeks on end. Inside a server case, GPUs talk to each other over NVLink connections at 1800 gigabytes per second. But a standard commodity internet connection processes only about 0.06 gigabytes per second. That is a 30,000 times gap in bandwidth. The sheer volume of data required to synchronize weights mathematically forces training into centralized data centers. This diagram illustrates the standard synchronization algorithm used inside those centralized facilities. It is called ring-all-reduce. In a data parallel setup, each GPU processes a batch, computes the gradients, and passes them along a tight loop. It is exceptionally efficient for bandwidth, but it assumes a latency tolerance of roughly 500 microseconds. Routing data across the public internet introduces latencies between 50 and 150 milliseconds. Apply standard data parallel training over those connections, and you incur a 100 to 300 times latency penalty before you even begin to factor in the throughput limits of the cables themselves. More complex methods, like tensor parallelism, where individual network layers are split, are completely impossible across node boundaries. They strictly require NVLink class speeds to function at all. The core failure stems from an architectural incompatibility, where the baseline physics of synchronous training actively punishes high-latency networks. Making this work didn't mean waiting for global internet speeds to multiply by 30,000. It required engineers to send significantly less data, far less frequently. This two-layer topology represents the distributed low communication learning architecture, or DiLoCo, published by Google in 2023. Instead of synchronizing gradients globally after every single step, DiLoCo breaks the rules. Individual worker nodes execute hundreds of optimization steps entirely on their own, using a localized AtomW inner optimizer. Only after caching those hundreds of local steps do the nodes finally talk to the rest of the network, using an outer optimizer to sync a highly compressed pseudogradient. That structural change results in a 500 times reduction in communication frequency. When combined with 8-bit quantization, total compression reaches up to 2,000 times. An algorithm called Sparse-LoCo pushes this mathematical bypass even further, and it serves as the engine for the Covenant 72B model. Sparse-LoCo uses chunk-wise top K selection. It looks at the computed gradient updates, isolates only the top 1 to 3% of the most important components, and quantizes them down to just 2 bits before sending them over the internet. The remaining 97% of the data isn't discarded. It gets carried forward locally via error feedback mechanisms, so the model still retains the accuracy of those unselected components. Other teams are taking similar routes. News research transforms gradients into the frequency domain, similar to how a JPEG compresses an image, transmitting only the low-frequency data to achieve up to 10,000 times compression. By stripping out the vast redundancy inherent in gradient updates, these teams reduced a seemingly impossible physical bandwidth bottleneck down to an incredibly tight software routine. This compression research gave rise to the first major modality of decentralized architecture, distributed pre-training. In March 2026, the Templar team proved this works in practice by launching Covenant 72B. They trained a 72 billion parameter architecture from scratch on 1.1 trillion tokens over 6 months. The entire process was distributed across more than 20 independent participants, coordinating their hardware strictly over standard commodity internet connections. Look at this benchmark table. The headline result is right here. Covenant 72B scored a 67.1 on zero-shot MMLU, narrowly beating the 65.6 achieved by Meta's highly centralized Llama 2 70B. To be clear, the centralized Meta model still wins on 5 of the other core evaluations, including HelloSwag and OpenBookQA. But the raw network performance is the point. During a 20-minute compute window, the decentralized cluster spent only 70 seconds communicating. That equals 94.5% compute utilization, running entirely on 500 megabit per second connections. Covenant 72B provides empirical proof that independent participants on consumer networks can coordinate tightly enough to generate a verified, downloadable language model. The second major architecture addresses a completely different bottleneck: federated learning. This solves the problem of training models on data that legally cannot leave its source, like hospital records or internal financial ledgers. Instead of moving the data to the compute, the training algorithm is sent directly to the local node. The data stays private, and only the resulting weight deltas are transmitted back to the network. A network called FLoC executes this using their FLoRa protocol. Since every hospital or bank might be using different hardware, FLoRa aggregates LoRa adapters of entirely varying sizes without introducing mathematical noise into the final model. And we know there is demand for this because it generates actual on-chain revenue through partnerships with medical institutions and organizations like the United Nations Development Program. But whether you are distributing pre-training or federated learning, you eventually hit the third architectural problem: verified training. How do you actually prove a remote node performed the dense calculations it claims it did? You cannot use standard cryptographic proof systems like ZKML to verify training runs because they add 4 orders of magnitude of computational overhead. The verification becomes heavier than the training itself. This diagram shows Jensen's Verde protocol. It bypasses the overhead using a 2-level bisection game. When a result is disputed, the timeline splits in half and then halves again, forcing the disagreeing nodes to narrow down their conflict to a single specific mathematical operation. Once pinpointed, a smart contract acting as a referee simply recomputes that single step. It confirms the correct state and strictly penalizes whichever node lied. That highly efficient verification is the critical bridge. It is the mechanism that allows decentralized computing to scale safely, relying on trustless mathematics rather than the goodwill of its participants. Despite the engineering success of these protocols, the absolute limits of compute still matter. Independent data from Epoch AI clarifies exactly where the market stands. Decentralized networks achieve 9 times 10 to the 17th floating point operations per second. Frontier data centers process 3 times 10 to the 20th, a 300 times throughput gap. Scaling protocols to 10,000 nodes requires 6 times more compute to match a centralized run due to synchronization overhead. Combine that inefficiency with the financial reality that centralized frontier training runs are rapidly moving from $1 billion toward $10 billion per model. When you look at the raw physical throughput and the financial density, a centralized network is never going to train a GPT-6 level model from scratch. But look closely at the growth trajectories on this chart. The centralized capacity is high, growing at a steady 5 times rate. Decentralized compute capacity is starting much lower, but it is expanding at an aggressive 20 times annual rate. Decentralized networks are built to supply the 99% of organizations who need custom AI architectures but lack a billion-dollar compute budget. These distributed networks directly serve enterprise requirements that massive, centralized labs struggle with. They enable fine-tuning on highly localized proprietary data. They route around divergent censorship restrictions, and they guarantee absolute sovereignty over the resulting model weights. The open-source checkpoint for Covenant 72B proves the architecture to serve long-tail demand is fully functional. 12 months ago, executing a 70 billion parameter run over standard internet connections was considered mathematically and physically impossible by the industry consensus. Centralized hyperscalers will continue to spend billions pushing the absolute ceiling of artificial intelligence. But underneath that ceiling, decentralized networks have successfully built the permissionless, sovereign layer for everyone else.